Welcome to that video. We are going to focus on generative neural audience field. So this paper, GIRAFFE, is a pretty nice paper that allows to generate 3D scene that are modeled, leveraging nerve model and to generate them in a compositional way. So what does that mean? That means that, okay, let's have a look at that sketch. But basically that means that we can generate, we can control the number of objects we generate, and we can control each object individually. So basically, this is a GAN model. So basically, a GAN takes some noise as input, Z, and then the generator takes the noise as input and produce some output. So here we take as input some noise, and we generate some output image. We're going to open the black box to explain a bit how that works. But here what's interesting is that the noise, let's call that latent variable. Those latent variables, they have some meaning. So for example, some part of the noise control the shape and appearance of the objects. Some other latent variable control the pose. So basically here that means that I can sample some noise Z that will control the shape and the appearance of my object. So here, for example, a car. And I can also sample the pose of it, and that will control the pose. And I can do that for multiple objects, and then the scene will be a composition of all those objects, and then I get an output image that composes my objects. So of course results are not so, that's pretty impressive in terms of what the framework is doing. The output quality is not perfect yet, but that's a paper that is, that was from 2021. In between there's been a lot of progress, but at the time that was pretty impressive. And that means that, for example, you can control very easily your objects. For example, you can keep everything fixed, all your latent variable fixed, but you can play just with this one, for example, to modify the pose of that object and to control where you want to place it. So that really gives you the power to generate like 3D scene and to control how you generate them. Okay, so we're going to to open the black box. I think I don't have much to say about that. So okay, let's move on to the next part. Of course we're going to review like some examples of what I've mentioned about the controllability of the 3D scene that you generate. So for example here they're comparing to another method, but maybe what really interests us is this, the result. For example, here that they've generated a scene, and by playing with the latent variable that control the triangle here, well, this 3D object, this cone, they can move it on to control its position and keep everything fixed, everything else fixed. So that's very powerful. Here they are making a circular translation, so rotating the cone around the cube. And here what they're doing, they're adding objects in the scene. So that really gives you a lot of power, a lot of controllability, and that is a lot of application in the real world. Okay, so let's open a bit this black box. If you are unfamiliar with nerve, I have a full course about it. I will put the link in the description if you're interested to learn more about it. But basically here, first what they do, they sample a camera pose. So that will be the latent variable that control the location of the viewing camera. Then we shoot rays in the scene. We shoot rays in the scene. So let's focus on one ray, DJ, it's the direction of the ray. And then we sample 3D points along the ray. So that's standard nerve practice. Then we have a bunch of 3D points for that ray. And then basically what we're going to do is to, so that's a first branch. Let's focus on the other branch and then let's come back to that. So basically we're sampling n latent codes on translation. So n will be the number of objects. The translation will be the position of the objects. On the latent code, I believe it will model the appearance, the orientation, on all the attributes of the objects. Okay, on here we have we have a kind of nerve that is responsible for each object. So basically the model h of θ1, for example, take as input the features for the first object, takes the position on the, well, here they are explicitly mentioning that they use positional encoding, which we know is critical for NeRF. So like a NeRF model, H takes as input the positional embedded position on direction of the ray, take also as input the features, and then predict. Usually with NeRF we will predict the color on the density of the 3D point, but here instead of predicting a color, we are predicting a feature map, well, a feature. So for example, instead of predicting only 3 values, we are predicting 128, for example. Then we have a composition operator that will aggregate all the information. The composition operator can be just the sum, a mean. It can be, for example, an attention mechanism that will compute weights for each of the features on the fly. But yeah, anything that aggregates the information. And then we have a single feature vector. So now we are agnostic to the number of objects. We don't care if we had 2 objects or 10 objects before the aggregation. Now we have a feature vector on the density of the 3D point. Yeah, and then what we are doing, okay, I'm just thinking about that. Okay, then we are doing the volumetric rendering. Sorry for the, basically we are doing the volumetric rendering. So we solve the volumetric rendering equation. So we are using all the points along the ray to compute the final feature for the pixel. So again, it's not yet a RGB value. With a feature vector for the pixel, and then we do that for all pixels. That creates us a feature map. So we create an image, but instead of having a 3 channel with a feature map, and then with a neural rendering operator. So basically a CNN based model, or that nowadays that could be a transformer based model that will transform the feature map into an image. So basically, in some way, this neural rendering operator, this CNN-based model, will allow to correct for artifacts that we might have from only using the NeRF-based model, the 3D-based model. Here we have a CNN at the end that cleans a bit the image. So basically, long story short, we can really see that as a GAN is input with some noise. This black box is a GAN that produces an image, and then we can train it with a standard GAN approach. We have a discriminator, with the generator on that left part, on the discriminator on the right part, and we can train it as a GAN. So that's very powerful because what we just need is a bunch of images. So images that are sampled from the data distribution. We don't need the 3D, the camera matrix of all those images. We just need a bunch of images and we can train it within a GAN framework, and all the 3D logic is embedded in the generator architecture. Okay, so here we have some more details on the neural rendering operator. Again, that's a CNN-based model. We don't need to spend much time on that. And I think that's all. We can have a quick look at the results. So here, for example, that's what I was mentioning. Here they are generating a car. Actually, I was saying that results were not so great, but it's actually not bad, right? It depends to what you are comparing to. It's true that we are in an area of generative AI where we see awesome results from a diffusion-based model, from, there are a lot of, like Sora, for example. But here, you can see you can rotate the object to generate. You can, here they do a camera elevation, change the appearance of the object, play with the depth. So basically here what they do, they mention what I believe what they are doing, they change the position of the viewing camera. So you can do a lot of things. That's very impressive. And again, you just train that from raw images without the 3D position. Actually, I'm not sure about that basically we could train it without without having the camera pose, but sometimes it makes training a bit easier to use the camera pose. We will need to double check in the paper. Maybe they do both and they compare the results, but technically if you had enough image you could train it without specifying the camera pose. Okay, we have a few more results. But that's it for this video. So I really hope you liked it. It was helpful to you. If you want me to implement the paper at some point and to describe the implementation on that channel, let me know. Let me know as well if you found the video interesting. Leave the thumbs up and subscribe if it's not already done. Thank you.